Okay, great. Hi everyone, my name is Omri. Unlike Yossi, I won't have a very nice and cool intro. I can't top that, I'm sorry. I'm currently the security research team leader at Ensilo. We are an endpoint security startup, and you can see what I do on our technical blog on breaking malware. You're more than invited to check it out. Today we're going to talk about user mode hooks and exactly how malware are bypassing them in order to achieve their goals. We're going to go over some technical background about user mode hooks, just to make sure we are all on the same page for those of you who are not familiar with the subject. And then I'm going to show you all the current known techniques. Just a disclaimer, none of them are my work. It's all stuff that other researchers did or stuff that are found in the wild used by malware. And to finish, I will show up a couple of new techniques that we developed at Ensilo. So basically, what is hooking? Hooking is used in order to intercept calls for functions, so we can change how they work and affect their operation to our own liking. The user mode hooks are extensively used in many security products and tools, especially at the endpoint sector. A lot of products tend to rely on it, mostly the newer ones. But the question we need to ask ourselves is actually why. So first of all, writing user mode code is considered more stable, more easy. It won't cause blue screens in case of an error, most of the time. And one of the other major reasons is that the fact that you just can, unlike the kernel, which on newer versions of Windows comes with some sort of protection, for those of you who are familiar with PatchGuard, so you can't just do whatever you want in the kernel itself. It's much more difficult for vendors. And for the last reason is that at user mode you got the full context, meaning if we take an example, web browsers, if you use a secured connection with SSL, so the data will be encrypted once it got into the OS layer. But before that, you can use all the data which is decrypted in the user space, like the URL, like the headers, and the response itself. So this whole topic of how to bypass user mode hooks exists for a very long time. I didn't invent it, but the last couple of years there's a significant number of new reports on this subject. More and more malware that use those kind of techniques and methods, and a lot of pen testers that show off how they bypass certain products that they have to that they come across when they do their red teaming work. So just to get basic familiarity with how a function call looks, if we'll see the following illustration, you can see two types of calls of different system services. We can see that there are a lot of points that we can decide to hook a specific function in order to change the result. And if we'll take a look on the right, we have a new layer that was added. It's more of a specific case for a 32-bit process that runs on a 64-bit machine. The operating systems use another layer in user space in order to handle this transition from the 32-bit context to the OS itself. So how can we actually hook the function? Like when we'll come to see how the memory looks like, what are we going to find? So I left the whole topic of the IAT hooking aside for this talk. You can go and check it out if you're interested, but it's less relevant because it's not very common among vendors. What usually happens is that vendors tend to use inline hooks, meaning they go to the specific memory region and change the actual code in memory of the said function. There are a couple of ways of doing that. The more common one is by using control flow instructions, such as jump or call. And basically, next, our function will look something like that. The hooked function is going to look something like that with a jump to our hook. And then our code will be executed, and we can decide to do whatever we like, change it, go back to the original function, or just return to the caller. Another way that we can hook functions is by generating exceptions, either with interrupts or on one byte patches that will create invalid instructions. That's usually the outcome of using a debugger if you're analyzing a malware dynamically. So this is what happens behind the scenes. Okay, so now we're going to start with all the currently known techniques. Basically, there's about 8 techniques. 6 of them are very common out there. We divided them into 4 different categories. The first one is secondary DLL mapping, which basically means that we are going to create a separate private instance of the DLL that we want to use, and that way it won't have any hooks installed on it. The first method that we can do it is just by loading the DLL ourselves manually from the disk. If we'll take a look at this illustration of the process memory, we can just read the file and then use reflective loading in order to make it actually executable and usable for us. And because we didn't use any actions, any type of APIs that the system usually use, no hooks will be installed. Reflective loading is a very known technique that malware use all the time to run code in memory. Basically, you can find a lot of implementations for it online on many open source GitHubs. The second technique is called clone DLL. Basically, we're going to create a new instance of the DLL on disk. We're going to move it to a different path. We're going to give it a different name, and then just load it as every other DLL. But because it will get a different name, it won't be hooked by the specific product that is installed. Since it uses the OS itself, the OS services itself, it's very good because it looks like a regular, like every other DLL, but it doesn't mean that its lower levels can't be, lower levels to it cannot be hooked by themselves. So the last technique for this group, for this category, is called the section remapping. Basically, we're going to create another mapping in the same process of the DLL we want to use, using the lower level native functions. We're going to create a section that represents an image, and then just map it once again in the process. That way, we still get 2 instances of the DLL we want to use, and it's pretty easy. There are a lot of drawbacks to this function, to this method. Some of them is because we only use the kernel part of the loader and not also its user mode part of the OS loader. The result will be that no initialization happens, so no dependencies are loaded, no internal initialization happen because the DLL entry point is not called. And the most problematic thing of all is because we map an additional section, relocations won't be handled. So if you get a complex piece of code you want to use, be aware that it might be faulty. This is due to a restriction of the actual operating system, but we won't get into that too much. So for our next group, for our next category, we'll do the system calls directly. Usually, what we're most interested in doing while we run on the machine is actually use the services that the machine provides, what the OS provides. So we're going to start up by looking at how the actual system call is done. On Windows, the calling convention for a system call is by passing the parameters on the stack and placing the index that represents the service that we want to consume from the OS on the EAX register. So usually what happens is that hooks are being placed on that instruction, and so we can't read the instruction, read the index ourselves from memory. But what we can do is build the stubs in our own code, use the syscall instruction in our own code, compile it in our own code, and then parse NTDLL, load it from the disk, parse it, and get the indexes themselves. And then we can do the same calls NTDLL provides. The second method here is called Heaven's Gate. Now, Heaven's Gate by itself is not a technique to bypass the hook specifically. It's more a byproduct of it. It's a very known technique for a 32-bit process on a 64-bit machine to do the transition to the kernel from the 32-bit context without going through the system itself, without going through the emulation layer that I mentioned earlier. And we can see for the example of the memory, space. And we have two cases here. The first is that the 32-bit DLL is hooked. So basically we can build a stub in our own code and jump directly to the native 64-bit NTDLL instance. And that's how we bypassed the hook. And on the second case, in case the 64-bit context is also hooked, we can do the same parsing we did earlier for NTDLL and do the call ourselves using the syscall instruction. The last technique in this group is pretty self-explanatory. It's called bring your own index. So up until now, if we had to parse all of this stuff in order to make it work, now we can just bring the index with us. For example, you can see here that there is a copy of the same function from Windows 7 on the left. Now, the issue with that is that you have to support every new DLL, every new operating system version that is released. So you have to maintain your own code. You have to be able to deploy updates. And if not, on future update to the OS, your code might break. The next category what we're going to discuss is called binary restoration, meaning that using some sort of memory manipulation, we're going to uninstall the hook. The first technique here, the method that is used is called reflective DLL refresh. Basically, what you're going to do is load a second instance of the same DLL. We don't need it to be actually executable. Using reflective loading, we're just going to load it. So we have the same code that should be originally on the target DLL. We're going to have a separate copy of it. And now we can see that we can basically do a bin diff between the code sections. And once we find a mismatch, we can just copy over the original code and basically restore it and uninstall the hook. So for our last group and the last technique, in the known ones, it's called code splicing, which is a pretty presumptuous name to byte stealing. Basically, we're going to build the stubs ourselves of the functions in different locations. We can just read the file, parse it, build the stubs in a different location, and then in case it gets hooked, we can just call the stub, we'll call the original function past the original hook. Okay, so now, up until now we discussed everything that is known, everything that has been done before. None of that was our work, but we decided it would be a bit boring to show only work of other people and not something that we did. So we came up with a couple of new techniques. There are actually more, but I had to cut it due to time constraints. So the first one will be used for for direct system call invocation. And if you think about it for a second, the same interface that the user mode has, the same native interface, the kernel also needs to support. So it has to be familiar with the same indexes, same services, everything else. So it basically means that the indexes in NTDLL also appear in the kernel itself. So we can just load it up ourselves and find the functions and the indexes ourselves in order to actually use them when we do direct system call. So there are a couple of variations for every system call. There is the NT version, which is the actual implementation, and there's the ZW version, which holds the actual index. And if in case there is the ZW version is exported, we can just get its address, and then we can try and look in that function for the actual index. Next, there is another case in which we don't have the ZW version exported, but we do have the NT version exported, like in the case of NT-add atom. What we can do here is, first of all, actually find the address for it. And now we need to find the SSDT itself in the memory of the kernel image. So basically, we can leverage the first method that we used in finding the ZW exports and the indexes to find enough candidates of both index and reference to the NT version. And then we can just scan the memory and basically find the SSDT without the symbol itself. Once we found it, we just need to traverse it again in order to find basically the reference to our target function. So you probably don't understand why I say kernel so many times when I talk about user space and user mode code. So you can load the kernel into user space also with the regular load library function. Some applications already do it. For example, if you're on Windows 10, then just look at the modules that are loaded by Explorer. I know why they do it, but I don't really know why they do it. They use a certain export for it to query the hypervisor, though they can just copy-paste the code into NTDLL as well, if they really wanted. The problem with this technique, even though it solves us parsing NTDLL itself, is that not all the system services are available for us. Not everything is actually exported, even though you can see in the list I compiled here. It's pretty useful. If you're a bit familiar with malware research, you can see that most of the functions here can be very useful for you. So for our second and last new technique, and overall new techniques, we're going to basically do a binary restoration, but now we're going to do it in a bit of a different way. First of all, we're going to look at the process, and if we detected that there is an actual hook on this target on the DLL we want to use, we can just basically capture its state, meaning that we'll go over on the private and writable sections where data was updated while it began running. We're going to capture their values and the current protections. And next, we need to refresh. We'll do the refresh action and actually remove the hook. We'll again use the NT-native functions. We're going to create a section for an image. And next up, we're going to unmap the original section, the original DLL. And we'll finish by remapping the section at the same base address. Thus, we'll have a clean instance of it. But if at this point we'll try and use it, things won't go very well for us, since, again, we didn't handle its initializations. So we just have to restore the state. So we copy all our buffers to the regions that are writable again. We have to restore the import address table, handle some of the exports operations. These are pretty easy tasks to do. Basically, it mainly requires mem move and mem copy operations. So this technique is pretty simple. to implement and use. And the result will be very much like the original operation of the OS. Not a lot of private pages for those of you who do some forensics work and stuff like that. Usually hooks won't be installed here at this point using those functions. But it does rely on native system calls, so you can't just use it as is for NTDLL, for example. And you do have to take into consideration situations of thread safety and stuff like that. So a couple of final words before we finish. Attackers learn how security products and tools work, and they adjust themselves accordingly. You can just try and Google protection against Mimikatz and see all the red teamers publications on this lately. I didn't get into it too much, but a lot of malware families are using these kind of techniques. Those are not necessarily sophisticated actors or APTs or stuff like that, but even the more common players are using it. Usually it's done only in the initial state of the attack, meaning they implemented basic code injection, process soloing, and from that point on, they are finished with it. They don't even care anymore if they are being monitored by hooks of some sort. All of those techniques are very easy to use, very simple, very trivial. Most of them you can just find code online. You don't have to do too much except for copy-paste. The MITRE attack framework, for those of you who are familiar with, for some reason, and I'm not exactly sure why, don't reference this kind of thing as a defense evasion. If you bypass user mode hook, they don't see it as malicious for some reason. And using user mode hooks for security is just not enough. This is just a beginning of a research we did on the subject. We're gonna release it later on, probably in the coming weeks, along together with more techniques and new classes of techniques. And the source code for the new techniques that I showed you today will be available on our GitHub probably this week. And any questions?